Good morning, everybody. So it's a pleasure to be here to be chairing a session where eminent speakers from various academic institutes are going to present their work related to numerical methods used for electromagnetic fields. Yesterday we had a very lively session on various aspects of electromagnetics from experts in various institutes and industry who shared their experience on how to effectively teach electromagnetics, and it was a very useful and instructive session. So I hope today also we will have a lot of instructive and interesting and enjoyable sessions related to the electromagnetics. So we will start the first session with entitled Overview of Numerical Techniques and Coupled Field Computations. The first talk will be given by Professor Udaya Kumar from IIC Bangalore on an overview of computational electromagnetics. Professor Udaya Kumar obtained his ME and PhD both from the Department of High Voltage Engineering, IIC Bangalore, from 1991 and 97. He worked in several projects related to defense at IIC and then EMRCs of IIC. He is with the Department of Electrical Engineering since 1998 and currently a full professor. His research areas include lightning and lightning protection, electromagnetics and high voltage engineering. He has been involved with design and analysis of lightning protection systems to Indian satellite launch pads and corona shields for India's first 800 kV fixed series compensation platform. He is a member of two CIGRE working groups, steering committee, member of Asia Pacific Lightning Conference, and research advisor to African Center for Lightning and Electromagnetics. He has been invited as an external thesis examiner in the University of Poitiers, France, Uppsala, Sweden, and Hong Kong Polytechnic. He was a reviewer for several international journals and conferences. Now I request him to start the talk. Thank you.
Thank you. Thank you, sir. Good morning to everyone. Before I start, I will thank Professor Kulakarani, my friend, for inviting me. I initially thought hardly 10 to 20 people may be there, because if you say a workshop on electromagnetics, response will be very poor. But yesterday I was really taken aback to see a huge crowd. Today I do expect some crowd. Let us see how it goes. Now, the topic what I have selected is a broad one. I don't know whether I can do a full justice. Nevertheless, being in academics for more than 16 years now, I had an opportunity to dwell with several numerical methods myself. Then I thought I should talk on the general perspective of the numerical methods and how and why they have to be employed in day-to-day application. The layout of presentation is as follows. We will be concentrating on item number 5 and 6. Other things are just passing remarks. Of course, yesterday itself people have highlighted the need for understanding as well as quantifying electromagnetic fields. We shall not go through those details. However, quantification is an essential process in any physics or engineering problem. Many of our students say electromagnetics involves a lot of equation, but to be very frank, everybody knows the property of the inductor, everybody knows the property of resistor, but they cannot, knowing the property, they cannot give any expression for the current, either qualitatively or quantitatively. They need to specify the property as it applies to each and every point in the time, then get into the governing equation, solve it. So for quantification, invariably we need equations. For electromagnetics also has some equation. We know that yesterday it was highlighted. I will not go through those details. The requirement of quantification of electromagnetic fields goes to the design of electrical and electronic equipments. Then in many of the fundamental and applied research, it may be new kind of processing of material, try to formulate new kind of materials, good or bad. Electrical engineers are dwelling into design of materials, which sometimes I have maybe very biased critic of the subject. Without knowing material, we are trying to design materials for pollution performance, for materials for tracking resistance, so on and so forth. And nevertheless, there is a good amount of research in Park where they try to subject the material into 100 Tesla or more to see the change in material transition. Likewise, very interesting applications are there where high electromagnetic fields are produced for various applications. Again, it was discussed in part in the yesterday's presentation. I will not go through those details, but most of the times innovation is only to cause destruction, because most of the innovation are because of defense research, and only part of which because of other research. So most of the innovation comes from here. Very sometimes very interesting, sometimes crossing the boundaries of civilian application. Then all of a sudden we had a new paradigm called electromagnetic compatibility. So too many electromagnetic devices used in an environment started talking to each other, like students talking in their class, not listening to the lecture. So then suddenly people realize it's not permissible. So we need to now ensure all equipment are electromagnetically compatible. Neither they should produce untolerable noise, same time they should not be susceptible to the. So this new paradigm is very important even for classical electrical engineering. Initially it was thought to be a subject of high frequency people, not really so. Now everybody has to worry about this. Then everybody has become health hazard. They are very conscious about their health, even though they don't do regular exercise. They eat the junk food, but it comes to the application, they say no transmission line should pass through my house. No, this antenna. Mobile everybody wants to use, but they don't want antenna in there. That's true. But thing is, health hazard is not that severe, but sometimes highly magnified because people think that's a very fascinating field. But we need to worry about this. All this application was there earlier also, before the advent of new computers. However, people are very wise then. They knew how to make good approximation. They knew how to use available techniques, lumped equivalent circuits, so on and so forth. So intelligence was dominating over the method for quantification. So they survived. We survived with the lumped parameter approach. However, now everything has to become very smart, very light, very efficient, so on and so forth. So we need to do a high degree of quantification. Otherwise, machines were there, radar was there well before the advent of digital computer. Anyway, now coming back to this now, it is also not required because we are going to numerical methods. I thought it should just pass through these remarks. Field have a definite structure. Fortunately, there are few number of layers. We have free or bound, charges or currents, or all of them. There's nothing more than that. Then we have salient properties because we borrowed things from vector calculus. These were developed by fluid dynamics friends, not developed by electromagnetic people. We borrowed things from fluid dynamics people, divergence and curl. The uniqueness theorem told if you know these two field is uniquely defined, then our people developed some gadgets to simplify the analysis or simplify the presentation of the equation. Then we have boundary condition, well-known boundary condition, mostly voltage and current, sometimes field. Then unfortunately, material interface has formed a boundary of its own kind because field quantities are discontinuous across the material interface. So we have natural boundary condition applied over there. These form the structure. Then comes this main point, because we are going to numerical methods, sometimes we trying to slightly tune it that way. Fields generally invade the space in and around, theoretically up to infinite extension. Basically, they are spatio-temporal function. They are function of x, y, z or any other coordinate system you choose to analyze. Then sometimes they are function of time. As a result of which, any function by classical definition of function theory, it has got a domain and a range. Both of them have infinite number of points. Domain has infinite number of points, range also. For example, if you say field exists in below a transmission line, you have x, y, z plane, you have infinite number of points in x, y, z, and every point has its own field voltage. So you have infinite number of values in the range, as a result of which, in the copying from the mechanical paradigm, we will say it has infinite degrees of freedom. This is a problem. It has infinite degrees of freedom. We are unable to comprehend the field directly. In addition to that, we have some coupling within the field, because electromagnetic field for quasi-static people, low frequency people, very happy. Charge is governed by voltage, magnetic field by current, and unlike the high frequency range, they are independent. If the voltage is there, charge is there. They are seriously dependent on the current passing through the conductor. Then we have current dependent on the load, which is not dependent on the charge on the surface of the conductor. But then slowly, when you go to eddy current problem, magnetic field, electric field start talking to each other. So because conductor has a good amount of free charge carriers, so coupling started, but that's okay, that's still tolerable. Then came the other problem. We have thermal field manipulating the material property, conductivity, permeability. Fortunately, permittivity is sensibly constant unless you select electroferrites. So the temperature modifies the conductivity and permeability, which we need to take into account in some application. Then came the another coupling, the fluid flow problems, or then movement was inward. There's a coupling between the kinematics and electromagnetic fields. Then there are some other additional coupling which have serious application in the energy conversion, but they have serious application in the sensing as a sensor and transducer. Now, before going to numerical methods, we shall quickly go through these. What is a solution? This is a classical question, but for limiting ourselves to engineering definition, here it's basically a function which satisfies the governing equation and all the boundary condition applied as well as natural. Then normally solution should satisfy all the continuity requirements what is demanded by the governing equation. The jumps and discontinuities are only limited to the boundary, most of the time not to the interior. Our classical model of point current source, line current source, point charge, line charge are models useful for evaluation of the field, modeling field, but they are not reality because they represent physical singularity. Anyway, so now we have enough continuity requirement. We have an analytical solution by mathematics people have told us that is it expressed in terms of elementary function. The basket of elementary function was limited to very commonly found one, then extended to series solution also later onwards. By definition, now elementary function or the function well understood, well studied, well documented. This is a definition given to by one of the mathematics friend. So then, what is so important about analytical solution is that all the parameters, it is the dimension of the conductors, dielectrics, even the boundary condition appear as parameters. As a result of which, no need if it is a change in the one of the dimensions or the applied field or voltage, no need to do anything, simply substitute there. So in other words, no need to calculate the solution again, so only substitute and get the answer. And more than that, they are also generic, differentiable and exact. And of course, we will see that these are very, very fancy items because they have their own limitation. Anyway, analytical methods are several in number. We have lost touch with analytical methods because first of all, mathematics is treated as a tough subject to be taken for passing the examination, whether it is in the undergraduate or postgraduate level. So we lost touch in that. Same time, you are also lost touch with analytical methods because maybe, in my opinion, which may be wrong because there are so many elderly people here, they may disagree with me. Mathematics should have been taught where it was developed. For example, instead of talking about eigenvalue, eigenvector, standing wave theory, natural frequency, the problem was started with the vibrating string. From vibrating string to start and get Fourier series from there, Sturm-Liouville problem from there, then your standing wave theory from there. I think most of the, at least applied physics and engineering people will appreciate. But it is taught as an abstract subject because mathematics want abstractness, correct? But that many, maybe people like us, we have limited capability, cannot appreciate. If you start with the physical problem, extend the mathematics, but extract mathematical formulation from there, it's fine because we have axioms in mathematics, we have physical reasoning or reality in engineering. They are the same, but put in different scale. Anyway, so we lost touch with most of the methods, so methods are not complete here, but we have lost touch with this. Why we have lost touch with this? Yes. Now let us, because you know to justify why you go for numerical method. What are the limitations of analytical methods? Most of them are hampered because our practical problems do not fit into curvilinear, orthogonal curvilinear coordinate system because partial differential equation invariably involves partial derivatives. These are the derivatives taken along constant coordinate surfaces. Partial means all other spatial and temporal parameters held the same or constant. So which is not really possible because most of the practical problems do not fit into orthogonal curvilinear coordinate system. There is a book by, I don't remember, which has described up to 32 orthogonal curvilinear coordinate system for Poisson's equation, but well-known things are only 3. But nevertheless, we can take it to be granted that orthogonal systems are not really possible for practical problems. Then we have non-linearity, inhomogeneity in practical problems. People working with machines will really appreciate, because our iron, great friend iron, is really non-linear. But when you solve numerically, it looks like a inhomogeneous problem, because every iteration you are solving a problem with mu r dependent on the position, so it is an inhomogeneous problem. Then came so many new things. Some of them I really know, some of them I really don't know. I know the title. So the stress carrying material, what is a dream of insulation designer. Then you have dispersion, both the blows. You have strange thing of chiral and metamaterials, which is most familiar to the high frequency people than low frequency people like me. Then we have cross coupling. We have movements involved. So one domain moves with respect to other domain, which is common in all rotating machines, actuators. Then coupling to thermal field, we have problems because we need to solve both the equations simultaneously. Then we have flow problems, solar. This list is big, we'll stop at this point. So in other words, analytical methods, very attractive, very elegant, but have limited practical application. So they are now limited to exploiting simple cases for explaining things in class, not beyond that. We have some semi-analytical method, first step towards numerical method. We also suffer from similar disadvantages. Now comes the question, if we summarize what we are talking about, we are saying that analytical method was very good and elegant, but has so many limitations. Then question comes, why? Then how is it that numerical method becomes an attractive choice? What is so special about numerical method which can tackle all this problem? So now let us, before phrasing numerical method, first thing we'll look at the limitations or the what you call salient problems in the numerical method. Variables, like geometry, parameters, material properties, and boundary condition, what is available as parametric form in the analytical solutions, they do not appear as in parametric form in the numerical method. One problem, one number, or set of numbers, not beyond. Then so therefore any change in boundary condition, geometry, materials, we need to do the calculation again and again, so on and so forth. Then comes the another important point, numerical solution is generally not exact except some trivial examples. Then many people raise their hand, why if it is not exact, how can I use it? But exactness has little practical relevance. All our measurements, whether geometry, electrical parameters or any other kind, have a tolerance or an error. So exactness has no practical relevance. Some tolerance is always there, so we have to live with that. And occasionally there is also an issue with the error. Some of the errors are not numerical in nature, they are actually imbibed by your correct or incorrect or partially correct modeling. So modeling error and numerical error must be separated out. So just introducing different colors to show that sometimes people club the modeling error with the numerical error, it's not so. In spite of all this limitation what we are listing, how is that numerical method is very powerful? To illustrate that, we shall go into two examples, very well-known examples, which actually is an attempt to show that numerical methods are relatively easy to handle for day-to-day application. Let us consider a simple concentric cable, inner conductor, outer conductor, very highly simplified thing. Then these are color pictures or equipotentials, don't worry about them. So if you really see now, we know that the electric potential does not vary with Z. If you fix the Z into the board, then theta is not vary theta, so it is a function of only the R coordinate. So potential is a function of R, is an analytical function which is a continuous function, therefore possesses infinite degrees of freedom. Even though you know how to solve this, but in general it is infinite degrees of freedom, it has a difficult mode to solve. On the other hand, if I make an attempt to imagine, because we always want to, we have inability to imagine something abstract, so always we want to imagine in terms of known things, so we shall imagine a set of capacitors formed between the equipotentials. Of course, just now equipotentials are known to me, otherwise you can do this approximation at a different kind. So we have set up capacitors, fictitious capacitors. Now, if you give this problem, most of the engineering students will definitely solve, because they know how to solve this series capacitors in series. Whether they are equal or unequal is not a question. They have the methodology because they have been taught to solve. What is the specialty of this problem? Number of unknowns is finite, because we have finite number of nodes. Those voltages form the unknowns. So here we have a problem where the unknown is a function of space which has infinite degrees of freedom, whereas here we have a approximate problem, the number of unknowns is finite. So in other words, this one we have been trying to solve, this one we are not so well versed to handle. So this is a difference now. We have one kind of problem with infinite degrees of freedom, other with finite degrees of freedom, where we are more familiar. A second example of this kind, so another example copied from some mechanical engineering book which long back, I don't remember. You have the famous hanging rope problem. So you have a continuous rope, it takes a pattern of catenary, minimal potential energy under the constraint that two ends are held at those 2 points. Then you can also have, instead of a continuous rope, you can have chain links, what is used in survey, which is made of straight segments with a joint, flexible, with the 2 degrees of freedom. The joint, the link can move around the joint. If you hang the chain of this kind, it also assumes more or less the same shape as the original rope. It is not really exactly the shape of the rope, but more or less the same. Is the shape assumed is almost the same. Now comes the difference. Let's see the difference with these 2 problems. A continuous rope, the shape taken by continuous rope is a catenary. It is a function of space, which if we take this as x, is a function of space. So it is, because it's a function, it's an infinite number of unknowns or infinite degrees of freedom. On the other hand, if you take the second problem, which is very closely resembles the first one, here the number of unknowns is finite. How is that possible? If you know the position of these joints or the links, then we will have the solution everywhere, because once you know this position, between these 2 positions it's a straight line. So therefore in the second problem, actual number of unknowns is y1 to y6, finite in number, whereas in the original problem it is y of x, a continuous function. So see the difference now. So therefore once again you can seek the minimal energy under the constraint to solve this shape. So if you come with these 2 examples, we are trying to use, what I am trying to highlight here is a continuous problems we are not well versed in handling, whereas discrete problem where number of unknowns is finite, we are able to handle. So now comes the crux of the numerical method, all numerical methods. So first point, repetition of what I have discussed earlier, field variables and their sources are continuous function of space and time. Now we invoke a process called discretization, where an approximation is sought for a continuous problem, such that in the limiting case means when you increase the amount of discretization, this will tend to the original problem. There is some theorem to show that convergence does not equal. So discretization process where we make an attempt to approximate a continuous problem to a discrete problem in a consistent manner. All numerical methods invariably invoke this principle of discretization, as a result of which number of unknowns come to a finite set we are able to handle using various techniques. Now coming to this concept of discretization, before I go further, there is a 2 main category of separation here called domain based method and boundary based method. In domain based methods, the governing equation is approximated, or attempt is made to approximate governing equation. We shall see them in some detail, not in full detail. So when trying to make an approximation of governing equation, what is the domain of governing equation? It is defined in the whole of the problem domain. Therefore your approximation is done in the whole of the problem domain. And remember, governing equation actually applies to each and every point in the domain. Therefore your approximation will be highly localized. Therefore you can see later onwards that such approximation is easy to code in a computer. Because your approximation is localized, it's easy to handle non-linearity and homogeneity. These 2 consequences we shall see later onwards. But what is this category has many methods: finite difference, finite element, finite volume, so on and so forth. We will name them later onwards. On the other hand, people liking Coulomb's law, Ampere's law and basic laws, they thought they should always deal with source, because if you know the source, you know the field. Then that invoked boundary based method. However, when these Coulomb's law, Coulomb's law especially started Coulomb's law, for example, or Biot-Savart law, they are designed for a hypothetical case of single linear homogeneous isotropic media occupying the whole universe. This is not practical. So then they invoked polarization, equivalence of polarization with the equivalent volume and surface sources. Then they went into this boundary based method. Basically, the philosophy is very simple. Is unknowns are the field as well as many times source, because when you apply voltage, we know only the voltage, not the charge distribution of the conductor. So therefore, if you can hold the charge distribution, somehow approximate the charge distribution, we will know the field. Likewise, here the boundary based method, we try to make an approximation to unknown source distribution, whether charge or current whatsoever. So advantage would be your approximation is limited to boundary, because unless you have a distribution of source throughout the domain, we have source only as the boundary most of the times. So your approximation will be limited to the boundary, and your solution will be smooth because you are using basic sources, so they will satisfy the governing equation almost exactly. So then we will see some of these methods, but before going, we will also have some disadvantages, because we are doing a global approximation, and if you have non-linearity in homology, it will be difficult to tackle here. We have boundary element method, Shah simulation method, method of moments applied to integral equations, so on and so forth. We shall see them there. In between, these, of course, it applies to high frequency also, but being a low frequency man most of the times, I will highlight this example. People working with rotating machines, they wanted rotation to be imbibed. Now we had non-linearity on one side, because iron is non-linear, same time we wanted rotation. And most of the times energy conversion occurs in the air gap, where air gap in induction motor is measured in fraction of mm. So when the things move, it is difficult to discretize and handle. They thought they should imbibe the good properties of domain based method as well as the boundary based method. So they invoked mixed method, where for non-linear iron they use the domain based method, for their boundary they use boundary based method, such that air gap need not be discretized, so movement can be artificially plugged in. But anyway, today's discussion is not important. I'll just skip this now. Now we shall now go into little more into the methodology. The goal is not to go into the details, because that will be covered mostly in the other lectures, especially the finite element that will be covered in the subsequent lectures. Here is only to give the general philosophy and superficial knowledge, and perhaps list out some of the advantages as well as disadvantages. At the same time, there are some methods hidden to insulation people, also want to bring them upfront because they have the same similar principle of formulation. So in no wave propagation, we have static, electrostatic, magnetostatic and Eddy current problems. For people from the physical mathematics background, they may like to call this elliptic problem and parabolic problem. Fine, there's no objection to that. We have several methods: finite difference method, finite element method, boundary element method, Shah simulation method, finite volume method, and so on and so forth. At least few of them, because I had to cross them during my work, I will show some result or something on that. And the list is not complete, please note, because there are several things which normally not used, several things which we never discuss in the engineering literature, but available in the allied literature likewise. So in this case, finite element method will be covered in subsequent lecture, so I will not delve into that in detail, but I will make some highlighting there. This boundary element method is a general paradigm. Sometimes all these methods, this Shah simulation method and the method of moments, can also be combined here. So I will not highlight this method separately. Let us go into the. Then we have wave propagation problems. Most of the times when you say electromagnetics now, it is mostly meant that we are dealing with high frequency. But remember, low frequency also requires a lot of electromagnetism. Here you have finite difference time domain method, a very elegant method proposed by E, which is extension of finite difference scheme, but it has got the physical insight to the curl operation. Then we have finite element method, because packages are available, they wanted to extend to wave propagation problem, but it's not really that famous. We have method of moments. Method of moments actually combines both the domain and boundary based method. However, invariably it is now quoted with the boundary based method. Then you have partial element equivalent circuit method, PEC, because people like circuit theory all the time. They wanted to represent everything in terms of circuit theory for two reasons. One is they like it and they can get some insight. Secondly, there are circuit solvers which can solve the matrix. Then you have got more things, fast multiple expansion method, which can do far field approximation, near field approximation. You also have finite volume method. Incidentally, I did not go through it. There's a PPT presentation from a professor from Aeronautics Department of IIT Bombay, which describes finite volume method for high frequency electromagnetics. I don't remember anything beyond this. It was there. I did not download, but I saw the name. Anyway, then we have transmission line method, which is another kind of extension from the equivalent circuit method. Then I have so many other things like this pseudo spectral time domain and multi-resolution time domain, so on and so forth. There are some methods borrowed from optics, and which I have no real expertise or knowledge. Anyway, now what we want to do is I will go through some of these methods, one or two in slightly more detail, not very in depth, but some of them very superficial, only to give a flavor of this methodology, because finally we are trying to quantify fields, so we need to know something more than a slightly a superficial knowledge. This because this can be extended to high frequency also, as I said, FTTD method. We shall start with finite difference method, not in more detail because this is very highly simplified numerical method which invokes some physical principle. Let us take two-dimensional or three-dimensional Laplace equation or Poisson's equation. It has Laplace operator on the left-hand side. This Laplace you can see now, as we mentioned earlier, these operators operate on when y and z constant. In other words, it is actually taken along constant yz plane. Similarly, this is taken on constant xz plane. These are decoupled because they are taken on orthogonal planes. This idea was invoked to apply or employ difference approximation to these. Please remember, difference equation was brought in the same time as differential equation. However, differential equation was more easy to handle because of continuum. Use a continuum, so difference equation left out. However, if you are dealing with ladder network, then we need to invoke difference scheme because it is also a very efficient approach. Anyway, difference approximations are sought, mostly center difference to preserve the order of the error. Then, so because these are because they are taken on the orthogonal planes, we can do this approximation individually without resolving Taylor series in 3 dimension. Even though Taylor series 3 dimensions are available, but we normally don't use it. So then what will happen if you replace the continuous derivatives by partial derivatives? Instead of continuous x, we'll have now discrete x because we are jumping in x by amount delta x. Between x and delta x and x and minus delta x, no information is available whatsoever. In other words, you are trying to now sample the continuous x by discrete set of x. As a result of which, when we do this operation on individual planes, you are trying to sample this 3-dimensional space or 2-dimensional space by discrete samples. So FTM comes from this principle, discretization, where continuous space is sampled at a discrete number of points, as a result of which we'll have a equation which is completely discrete in nature. For example, here when you take this 3-dimensional grid, this approximation to z using these 3 grid points, approximation to y in these 3 grid points, approximation to x in 3 grid points. Interestingly, finite difference scheme or a Laplace for the Laplacian operator or Laplacian equation invokes mean value theorem, one of the elegant properties of the elliptic problems or the electrostatic problem. In the source free region, the potential at the center of a sphere is average of the potential of the surface of the sphere. This is consequence of 1 by r dependency, 1 by r square dependency. So this is inbuilt here in a discrete version. So now this is well known, especially for giving assignments to the student because they can formulate it in ease. So this could be one of the first step or first method what we can teach and what we can expect from students. However, let's not be taken away by this approximation because occasionally, even in research paper, they do this mistake of inconsistent approximation. Finite difference scheme in the classical approach cannot model interface because in the interface field is discontinuous, your approximation is not valid. Maybe we will not go to details. If required, we shall see later on. So therefore, if you have only one material, you can proceed. If you have multiple materials, you need to take care. So what we can do instead of doing this directly, we know that the governing laws are actually the basis for differential equation. In the Laplace electrostatic field, we imbibe two basic laws. One is conservativeness, one is Gauss law. The conservativeness can be directly satisfied by defining grid points, any grid points. So therefore, we need to impose Gauss law. So if you have multiple materials, you can impose Gauss law and get a consistent form of the FDM equation. There are some intricacies required to handle boundary and all. I think today's discussion may not be appropriate to go ahead. Quick example. This is a classroom example. Palpate capacitor in a cylindrical geometry. Incidentally, there's another issue in some of the presentation made by people who use numerical method. When you select a cylindrical coordinate system, minimum value for R is 0. You cannot show result on the left side. Some people do it, it's very strange. Because cylindrical coordinate system, you can you either whole 3-dimensional picture or a 2-dimensional picture which starts from R is equal to 0 only. You cannot go beyond it. Anyway, so now this is a well-known example. You can visualize this FT. But this is a practical problem. We have got cables now, especially HVDC cable. These cables have XLPE insulation because easy to extrude and good dielectric properties. Unfortunately, DC insulation is a problematic case. Many a times, even in even in big organization, DC is taken to be granted. It's not really so, because in the case of DC insulation, after a few minutes to few hours, the field will change from dielectric to conduction field. During this process, there is a problem because except porcelain, except glass and some well-known material, polymers and many such materials have a inhomogeneous property, non-linearity property, not inhomogeneous, where conductivity is a function of electric field as well as temperature. Not a simple function, exponential function of the temperature and electric field. So sigma becomes now it's a function of field, and field is a function of space. As a result of which, it so happens that the field distribution normally, I'll come back to this example again. In the normal dielectric field would have been showing a pattern like this, where field is highest in the outer surface of the inner electrode and falls down. On the other hand, in these materials, field can be highest at the other end also because of the temperature as well as self-corrective measures. What basically happens from the field point of view? What basically happens from the field point of view is that there is a space charge accumulation coming naturally in the material. So as you charge slowly, space charge trickle into the matrix of the material and accumulate to cause this changeover. However, fortunately, to solve steady state, we need not worry so much, but about this space charge, you can directly solve the inhomogeneous part of the conductivity, taking both sigma del square phi as well as gradient sigma dot gradient of phi to solve this. So what has been done here is, instead of, this is a well-known problem documented, but I wanted to know what will happen when the conductor is slightly eccentric, because conductor will have slight eccentricity during the extrusion process. Also, you can have small minor irregularities. First, as a first step, we took the eccentricity. Here is highlighted. So we thought we shall go with the finite difference scheme. In this one, of course, to generate, you needed orthogonal grid. So generating orthogonal grid is also a problem, and sometimes students are also problems, because I respect my students because they are dear friends. However, when the placement is done, they have very low interest in the project. So they hardly give any interest, because they know that some grade they will give. I have already got the job, why should I worry? So now how to make him to get the orthogonal grid for this problem? Then I said not possible with him. Simple, take this is a field distribution around a line charge. If you look at the field distribution, two parallel lines, positive and negative, the equipotentials as well as field lines are part of circles. The equipotential forms complete circle and field lines form part of circle. So I use that to generate an orthogonal grid. Here what is done is, we solve the coupled thermal electric problem. So instead of solving directly, please less than a sluggish partner like student, what is done here is, this problem is converted to a circuit problem using impedance network method. It is a derivative of the finite difference scheme. Basically what we do is, instead of solving the equation directly, we can invoke circuit principle, then go to a circuit solver and solve it, like SPICE or otherwise. So for electrostatic, we have these resistor which change their property by every iteration. This is a thermal equivalent where you have sources at every node and thermal resistance coming into play. So, one of the examples. So, here I have tried to invoke the scheme of impedance network method, which is actually a predecessor to partial electrical equivalent circuit and transmission line method. Then, so we shall summarize quickly the advantage, disadvantage of FDM. Very simple to code, but simple to code in the sense, if you know how to use basic how to write basic functions and how to organize variables, it is simple to code and easy to understand, evaluate error bounds. There are a lot of literature which gives you the error bounds, minimum amount of calculation, and to some extent non-linearity and inhomogeneity can be handled to some extent. But the basic disadvantage comes with the orthogonal grid. We need an orthogonal grid to do direct FDM approximation. However, if you use the integral approximation, you may partly overcome this problem. So, but in classical sense, yes, we need orthogonal grid. And problem when it has smooth boundary, which is not conforming with the coordinate system what we have employed, we need staircasing error. In other words, imagine a Cartesian graph, a grid, we are trying to model a concentric cable problem in a Cartesian grid. Obviously, grid lines are straight and boundaries curved, so you need to do a staircasing approximation. This is also a serious problem. Then solution is available only at sampling points. So this is one of the basic problems in FDM. Method does not tell you how to interpolate or extrapolate. You may do it on your own, but method in principle do not speak about any of these things. Then local grid refinement is not possible. One of the biggest headache here. It leads to large matrix, but a very sparse matrix. Field evaluated not smooth, especially some of the application where field is important. This is a very critical point because field evaluated not smooth. Then open boundary. This is another issue. We in electrostatics we don't have open boundary. We have only open geometry problem. However, in literature you are violating the mathematical principle which is called as open boundary. So we shall continue to use that terminology. Open boundary cannot be directly handled. So what we have to do is we have to bring in methodology from FEM to handle that. That's the one. So now in the first section I have now just we went through FDM. Let's have a little more details and we summarize advantages and disadvantages. Now we shall go to the next one, very famous friend of us, finite element method, again borrowed from our civil and structural friends. Here the philosophy is slightly more elegant than finite difference scheme. I will not go through details as I told you, but some of the points need to be highlighted because most of the industry uses FEM rather than any other methodology. Even though there are commercial packages, engineering design involves electrical, thermal, mechanical. So it is a common platform for all the three disciplines, therefore FEM still the leader in this domain. So we shall simply go through the basic essentials, not the details. So now what is we have to see? Any numerical method, when you look into the method, what we have to see is the principle of discretization. How is the approximation done for the continuous problem? So what is done here is unlike FDM, here we try to do a approximation to the whole of the domain. For example, here again we invoke grids in the domain. Let's take the one-dimensional example, concentric cable. Potential varies only along R. So we try to make an approximation. One of the approximation possible is we assume that potential varies linearly between these nodes, or every interval has a linear potential variation. You may choose quadratic or higher one, but this is one of the basic formulation. You can use higher order modes also. What will happen now? If you make such an approximation, your aim is to get the solution which is specified for the whole of the domain. However, unknowns are still limited to the nodal values of the, and because the nodal values are known, we know the solution everywhere. In other words, in this approximation, continuous function phi is approximated by discrete function which is defined at the nodes. The extension to TD is obvious. This triangular mesh is, most of my presentation will have result derived from the coding in MATLAB, not from MATLAB, coding in MATLAB, except this is MATLAB has a PDE tool, which normally I don't use, but for putting this figure I use a PDE tool in MATLAB, but I don't use it. Maybe I am not familiar with that. So here, if you have two-dimensional thing, what we can do, same principle. Here, because we have two-dimension, we need to approximate by polygons. Here, triangular polygon is very famous in the early days because automatic discretization was available, and discretization was always ensured because of the mathematical principle. So if you see here again, the vertices of this triangle will have nodes. The potential of those nodes are assumed to be the basic variable. Once you know the potential of the nodes, potential everywhere within the triangle or the polygon is approximated suitably using consistent polynomials. So once again, if you do this, two-dimensional function is approximated by set of unknowns defined in the two dimension and a known interpolation function. So likewise, if this approximation is carried out, this is only an introduction, not the detail. So what is the thing now? Because you have made an approximation to the unknown function, which is called the potential here, original differential equation cannot be employed. Original differential equation is a Laplace equation, in this case, or Poisson's equation, requires the second derivative should be definable. That means first derivative must be continuous, otherwise we cannot define the second derivative in this case. So because we made approximation where PD cannot be employed because we have can have lot of discontinuities. So then people said we get weak solution or solution again. However, project to a domain whose dimensions are much lower than the original dimension. So in weak solution, we get the solution. However, it may not satisfy all the differentiability and continuity requirement. So here we have two distinct approach. Very elegant approach, in my opinion, will be variation calculus. We will not discuss that, but very beautiful one, which was developed along with the differential calculus by the same set of people, Newton and others. But we have lost touch with this because slightly more difficult to understand because we've never had a training in this. However, if somebody is interested, therefore, learning, you know that distance between 2 points is a straight line. But can you prove that using your differential calculus? Distance between 2 points, you know. I'm not talking geodesics, I'm talking about plane surface. It's straight line, everybody knows, we can show it geometrically, but can you prove it using differential calculus? Such formulations are straightforward in variation calculus. So earlier part of FEM was based on variation calculus using extremization of energy, physical energy, sometimes artificial energy, because we need to invoke, for additional terms we need to invoke a concept of energy. On the other hand, more straightforward, more general approach was possible using the MOM, method of A residues. Basically it's a MOM, method of moment, in which Galerkin formulation has ruled over the finite element method across civil, mechanical, electrical domain. So most of the times people follow a Galerkin finite element approximation for invoking a weak solution approach. Earlier days we used to have variation calculus approach. Then we will not go to details, as I told you, there will be 2 more lectures which will deal with these. Now once you do this approximation, we get a algebraic equation, once again like FDM, which can be solved using various techniques. Because they are sparse matrices, normally we don't solve them directly, we solve them using iterative technique. Now before concluding, sometimes there is occasional confusion in low frequency people. So now that I thought I should just put this slide. So basically elements are subdomain in which we make approximation to unknown variable. Now you have got classification here, nodal or scalar, very famous type, where the elements basically can support divergence, not curl. But when you use large number of elements, it can be overcome. You have edge or vector elements brought in because when you use electric field or magnetic field as a variable, we need to satisfy the discontinuity. So this was brought in. But if you really see, this is more famous with the eddy current and wave propagation problem, whereas this is famous with the general class of problem. Then we have classification according to dimensionality of the element, because a 1D element can be present in 2D, it can be present in 3D also, likewise. Then order of the interpolation problem employed. I think that will be covered later onwards. We will not. Continuing there on, something more. Of course, nodal element formulation is available for scalar and vector fields. Electrical engineers are very familiar with this. Edge element formulation has come recently. More than that, there is something more. There are problems where relative movement of conductor is involved. It may be movement of containing fluid or a movement of a platform or a rail, so on and so forth. In those cases, these finite element schemes have numerical problems. So that has given rise to what is called streamline upwinding Petrov-Galerkin formulation, other kind of formulation. Then something more, I think we will skip this. Now this example, this is a code written in MATLAB, not the MATLAB toolbox, code written in MATLAB. This is for the flow of liquid sodium in the breeder reactor, fast breeder reactors. To evaluate the sensitivity, the flow meter basically has a simple concept. We have liquid sodium flowing in the tube, steel tubes. You put magnetic field using permanent magnets. So because there is a movement of the conductor in the magnetic field, it will cause a circulating current. You take diametrically opposite points. For example, here these are the full shoes. We put diametrically opposite point, put solder there, take it to a millivolt meter. The millivolt what you measure is proportional to the flow rate. So in order to evaluate the sensitivity, they want liquid sodium cannot be stored. You cannot use ordinary flow meters there. So they wanted to use this magnetic flow meter. They are using it, but they wanted to know how to calibrate. This is a code written to IG card. So here magnetic field calculation is done to the method which I am going to describe later onwards. This is 3D FEM code, which is using 27 node brick elements, serendipity brick element. And these are the induced voltage profile and vector potential profiles. And as I told you, flow rate is nominal. For the present flow rate employed in India, this is sufficient. And in case you go for a huge production, a huge reactor, then we will have a large magnetic Reynolds number, in which this Galerkin scheme can lead to oscillatory solution, for which streamline upwinding scheme can remove the oscillation. Those details are not essential today. Now we'll go to the next one. So summarizing, finite element method is still a dominant method because it is used in our allied branch, civil and mechanical. Engineering design involves a combination of all the three disciplines, so therefore finite element method will still dominate the industry in most of the application. It has been developed to such an extent that it can handle even the open geometry problems or open boundary problems. Earlier Ballooning technique was employed, now we have a special element called infinite elements to model the open geometry. Then it also has different forms in the form of meshless formulation, so on and so forth. So in other words, FEM is one of the important numerical method for electrical engineering. So next method will be the finite volume method, which is not that famous in electrical engineering. Some people take it to be the extension of finite difference scheme. Basically, it is not something new. What is done here is basic conservation laws are directly applied. For example, in a discretization scheme like this, you need to employ Gauss law or the divergence law directly. So that gives you the formulation. I'll not go to the details, but this is a interesting methodology because easy to understand, easy to formulate, and sometimes not always easy to code. Let us look into this problem. Here, this is remember x and y are not to scale. This is only 20 centimeters. This is 4.5 meters. This is a 400 kV AC RAP bushing. Now, geometry is not to the scale, but it's only for some study. So, in order to study the temperature and electrical field distribution, the only problem was RAP has a conductivity which is a function of electric field. So, therefore, we want to know whether it can lead to relocation of the highly stressed region. So, electrical analysis and the thermal analysis are carried out in the finite volume method. In finite volume method, convective boundary condition is imposed here because it's a very strange one. In electrical engineering, we don't have a counterpart of this Churchill boundary condition or convective boundary condition. Here, you can also see that there are stress grading foils. Location is not correct, but adequate for the study. So you can see stress grading foils are trying to equalize the electric field distribution, but thermal they are not effective because thermal conductivity is not high. So this was employed for a specific purpose. Now I think I have listed out the advantages and disadvantages, but basically because it is a domain based method, it is not designed to handle open boundary. We need to do some further modification. It leads to large and sparse matrices. Now we'll go to some unconventional methodologies where actually method of moment is brought into classical insulation application. These applications are not readily seen by people working in magnetics because they are not that useful in handling non-linear materials, but nevertheless they are useful in many senses. So I will quickly go through this because it can give the basis for method of moment for higher frequencies. As we know, basically free and bound charges produce electrostatic field. Free and bound currents go to magnetostatic field. Here bound means that is arising out of polarization of the material. Now there is a theorem in electrostatics as well as magnetostatics that effect of polarization can be translated into effective surface and volume charges depending on the inhomogeneity. And once you know that, we can apply Coulomb's law and evaluate. Basically, we don't electrostatic problem. The charge distribution of the conductor is not known. If I make an approximation to the charge distribution, then I can evaluate the field in terms of the coefficient of the charge distribution. I will avoid the details here. So now, but unfortunately, like any method of moments, it involves complicated coherent system transformation, numerical integration, handling singularity, because on the surface you are trying to evaluate the potential. Analytically, surface charge density has it has potential and electric field which is free of singularity. But you do numerically because you are trying to approximate Riemann integration. Singularity comes into picture. We need to do some circus for handling that. But advantage is you are trying to approximate for the unknown source, as a result of which your solution will have satisfy the Gaussian equation exactly. This is a typical 400 kV corona ring. The interest was not the corona ring because these are readily available. What level of surface abrasion or protrusion can be tolerated so that in spite of presence of such protrusion, corona will not appear in the system. That was the aim of this study. So this was done, and micro and millimeter scale protrusions are invoked and the field was evaluated. This is one of the useful methods for electrostatics. And the next, of course, this is another counterpart of the again surface charge simulation method, where the potential distribution along the string insulator is evaluated. But I am coming to magnetic problem. Surface charge simulation method can be invoked in matter statics by invoking fictitious magnetic charges. So you have iron pole, and you have got this is permanent magnet, permanent magnet. These are the pole shoes made of soft iron, and invoking again the similar principle, we are able to compute the field. So these are something useful. To handle non-linearity, we need to now invoke the volume charge, fictitious magnetic volume charge distribution. Another example of surface charge simulation method comes from the grounding problem in Karnataka, maybe in other part of South India, I don't know. Of course, availability of land for substation has become very difficult. Land, because land is very expensive, many people don't want to have substation next to their doorstep. Second thing is, so now government gives you land which is not flat. Substation runs for 200-300 meters depending on the voltage level or more. In such cases, it has found that working on the land, make it flat, is very uneconomical for several reasons. So what they are doing is, each bay of substation is different ground level. In such cases, what will be the performance of grounding system? So in analysis, some code was written. Again, it uses surface current simulation method. The current is fictitious over there. So this has got these advantages, and this one what I have listed here can be extended to higher frequencies also. What advantage of this method? It involves only boundary discretization. Can handle open boundary because the domain never comes into the discretization. It's very accurate, and small aberration surface can be handled. Mesh refinement can be possible. However, it has got its own limitation that codes are difficult to write, especially if you are looking for micro irregularities. Then only sources are found. All the boundary based method computes the source. So then solution you have to compute on your own. Non-linearity in homogeneity is difficult to handle. We'll quickly go through other alternative of this because many of the people may not be interested in this. So in the previous case, surface charges approximated, but because of which we have a problem of doing surface integration, we have problem of handling singularity. On the other hand, if I can combine all of these surface charge with discrete charge and keep it just inside the boundary, then we can overcome all the difficulties. So it has got several applications. We can model buildings, launch pad, these Corona Shilpa platforms, so on and so forth. It has similar advantages and disadvantages. Now, so those two are mostly static problems. In eddy current problem, I think we'll discuss in the next presentation. So what I thought was, we'll just go through only one slide on eddy current problem. In eddy current problem, we can have frequency domain or time domain, as you know. Only problem comes because time enters as a variable in the case of time domain version. So then many of the methods can be employed there, where spatial discretization is still remains the same. Only thing is suitable time discretization or time stepping is required. Most of the times, this time stepping is done through either explicit or implicit schemes, where explicit scheme has the beauty that every time updating can be done without matrix inversion unless you have a non-linearity in the system, whereas in the implicit scheme, there is no numerical instability. However, matrix inversion may be required at least once. This is an example looking into the current distribution through tower legs. Tower leg, you have L section, T section, plus section depending on the cross section. So here the current distribution was computed using the in-house eddy current solution. We shall summarize the low frequency method before going to high frequency methods. There are several well-known methods. Selection of method must be based on the properties of the problem, whether it is open geometry problem, whether it has inhomogeneity, whether it has non-linearity, one thing. On the other hand, what is your target? Are you talking about the total energy, force, capacitance, inductance, or you are looking at a maximum field, peak loss density in a certain region? Depending on that, you can choose the method if you have a choice. Then, of course, it's important to check whether field computation is part of a physical modeling process, because field computation may be a main step in the design process. On the other hand, if you're doing research, it may be part of a model which involves modeling a physical process. So then we need to do the things repeatedly. Those issues must be discussed or analyzed before taking it to a problem. Application of frequency methods are very vivid. We know that. We'll skip this because the time. We'll go to high frequency method and dwell into one or two high frequency method before we conclude in this presentation. Now, in the case of high frequency method, we have got a frequency domain approach, time domain approach. Most of the times, it is a proprietary term of your ECE people, electronic communication people, rather than classical electrical people. However, electrical people sometimes have to deal with that because they have got strange phenomena. We will mention about that. Now, question is, here you can formulate in terms of potential and field, modified potentials, so on and so forth. Now, in most of the times, in the high frequency method, we invoke what's called method of moments. Actually, Galeckin approach is also a method of moment, even though we don't call it by that name. So anyway, in method of moments employed for high frequency, we can do approximation using domain-based method or boundary-based method. But what is the speciality here now? I think this could be boring. I think I'll skip this, even though it's very interesting. I'll skip this and go to the next one because too much of abstract without any example would be. Basically, what we do here is the following. In the case of method of moments, like your Galeckin finite element method, we do approximation. In this approximation, for the unknown source or unknown potential, we invoke what's called basis function, and these basis function define the order of the approximation. Then we use another function for sampling the residue or the error. I think I'll skip this also. Okay, we'll go to this example that may be slightly better off. Let's look into the method of moments for thin wires. Thin wires are a bit famous in the modeling because prior to the surface modeling, thin wire modeling dominated evaluation of radar cross section, evaluation of the interference, so on and so forth. Here the example is specifically for frequency domain because time domain frequency domain difference comes only with the time stepping. In all these problems, most of the, as I told in high frequency, a method of moments invariably means boundary based method. We invoke Green's function or the fundamental solution. This is nothing special. We had point charge as a building block for electrostatic field. You have a dipole as a building block for the high frequency field. However, finding the solution, fundamental solution of the Green's function for a particular problem can be very, very cumbersome process because problem is not having only one material. Problem is having multiple conductors in and around. But other than that, this method goes. I'll avoid all these details. So what we try to do here is that the unknown current in the wire is approximated in terms of simple pulse function or triangular function or a combination of polynomials, and then try to impose boundary conditions, because once you make an approximation of the current, we can calculate the scattered field, but field on the conductor inside the wire should vanish or it should be equal to the impedance drop or resistive drop. Using that we can build a set of algebraic equation, and for most of the electrical engineers, if not the electronics people, they can avoid all these things by using public domain code called NEC. So this is a quick example in-house code where dipole impedance of the dipole antenna is calculated. It involves very minimal steps. If you really want to try, it does not require any great mathematics. You can evaluate the impedance as well as current distribution, or else if you are not ready to write code, you can use the numerical arithmetic code which we employed for calculating the lightning surge response of the tower-like structure, integrated tower structure, and so on and so forth. Only problem in the frequency domain to time domain is the conversion from frequency domain to time domain, which involves a lot of numerical problems. Then another thin wire version of our code. Here what is interesting is the following. In most of the times when the field evaluation is made, it is only one step analysis. However, here we are trying to model a physical process. You have got a descending leader, the rating leader finally strikes the ground. We have a tower which launches upward leader. All these events happen in a fraction of a millisecond. If we don't have the upward connecting leader, it is like a vertical monopole over a ground. So this strike to ground induces a current because it radiates electromagnetic field which links to the tower-like structure and causes a ringing within the tower. On the other hand, if you have got an upward leader, it is a non-linear electric arc which has a corona sheet surrounding it, spanning up to few meters, which will dump in the charge, as a result of which the current from this form changed to this other form. So this magic was possible because the field computation was done in time domain using thin wire code. This principle is extended into the conducting surfaces in the method of moments using most of the times what is called RWG basis function, Rao and other two names I don't remember, obviously not Indian names anyway. Basis function, which is very famous, which ensures continuity across the surface. And again I will avoid all these details just to show that even electrical engineers also do some such calculation. This is not mine, this is the only example which is not mine. Here we have got partial discharge, which is one of the troublesome thing in the electrical equipment. When you talk about the gas insulator substation, presence of floating conducting particles can initiate a discharge, which is very essential to detect, otherwise you might have to shut down the substation. So these can be detected automatically because these discharges, actually electrical discharges arising out of corona or arising out of floating particles, have a rise time which is measured in nanosecond. The resulting current has a rise time measured in nanosecond, tail time measured in few to tens of nanosecond. Obviously, because rise time is very fast, it will travel as a traveling wave along the conductor, and there's 2-3 different modes are possible. Basic mode is TM, then dielectric surface TE, so on and so forth. So because this is a continuous duct where measurements are possible only at the couplers, so some things are done in the electrical engineering also. Now I avoided all the things because I think that the explanation would be boring. In the method of moments, basically we discretize the boundary. It is we have a counterpart in electrostatics, matter statics, eddy current, and high frequency. But in high frequency, it is always mostly associated with the boundary discretization. The resulting equation is simple algebraic equation, linear for linear material. It is a small matrix, very dense. So in method of moments, because boundary is discretized, boundary conditions most of the times are built in. This is best suited for linear system. Disadvantage is that first of all, we need to have a Green's function. We need to handle singularity, because the numerical version of the equation has a singularity. Difficult to handle multiple materials, we need to do a lot of circuits. And numerical effort is proportional to cube of number of unknowns. We will quickly go through other one, this finite difference time domain method, because previous method was difficult to understand, but this will be very straightforward to understand because it's a direct implication of Kerr law both in space and time, called E's algorithm. Basically, we have coupled equation. So instead of combining them, we'll handle them separately in this approach. So this it's an example in Cartesian grid. So you try to employ central difference for the space and time using leapfrog technique, for example. If you see here now, magnetic field here is a result of the circulating electric field here. And because time is involved, this is leapfrogged in time by half time step. In other words, the magnetic field at the center point, surrounded by 4 electrical sampling points, will be given by the components surrounding curl of this electric field. But please note, these are defined at time t, whereas resulting magnetic field will be having an increment of delta t by 2. This is even though physically correct, it is a numerical forcing of propagation or time delay involved. This is a very simple one to understand and implement with a current Friedrich-Lee the condition for stability. Because it's an explicit scheme, we cannot use large time steps because numerical domain of dependency should contain the domain of dependency of differential equation. Otherwise, numerically it is an unstable system. So this has to be invoked. So now why I'm trying to propagate advertise this method? Very simple to implement. However, we have to not be taken away by simplicity because it can invoke numerical dispersion and anisotropy. This is very well known for people working with the high frequency because this dispersion is not from physical phenomena, it's from the numerical aspect because of discrete sampling. So remedy for this will be to have at least 10 cells per significant wavelength component. If you are working with frequency domain, defining wavelength is not a difficult one. If you work in time domain, you need to take a Fourier spectrum and decide which is your significant upper frequency for which we can get the wavelength and ensure that 10 cells are there for every significant wavelength. Then opening of the approach, this is okay. Now coming back to this one mostly will not encode, but here we have a problem. So when you have thin wires, you need additional effort. And because it's a domain-based method, you have to discretize whole of the domain. Because of which, when you have open boundary problem, we need to truncate the domain because we cannot handle infinite domain. So truncation can be done in several means, by absorbing boundary condition or higher order differential operators. I will skip this also because a small example here now. This is an old example of mine where instead of talking about RCS, instead of talking about the antenna power radiator, we have a channel, lighting channel of 1 centimeter radius, 3 kilometer long. Please note this is a very long one. So the whole space is discretized up to 9 kilometers. Perfectly matched layer is employed to the boundary, and our cell size will not permit to handle 1 centimeter radii conductor. Using subcell subgrid approach is possible to implement. What is done is excitation is given. Most of the electrodynamics, when you do time domain calculation, you should avoid any wave which is any signal which is rising fast. You should have a smooth rising signal. So what I did was using Gaussian rise, sinusoidal excitation was given at the ground end, wait up to steady state and compute the impedance for various frequencies. You can see theoretical and computed impedance match pretty well. So it shows the method is excellent. FDT method can be very accurate. So now to highlight the methodology, numerical effort is proportional to n, whereas an earlier method is nq. However, because domain has to be discretized, n can be pretty large. When you have multiple materials, not a serious issue, but if the materials are not fitting into orthogonal planar interfaces, we have some problem. And this method by itself is not suitable for far field approximation. Interaction between two conducting or dielectric bodies separated by a large distance, not suitable for system with high Q, and so on and so forth. I think this also will. Now I'll quickly go through two more slides before I conclude. In the high frequency method, there's one called transmission line method. It is again a derivative of impedance network method or partial electrical equivalence method. This method basically imagines a skeleton of small transmission line which is representing the original problem domain. So everything, the field propagation in the original domain is now imagined in terms of signals propagating in the small transmission line which are interconnected. So it has a beauty that we can use circuit solver for solving the field provided we get the original matrix. And there are two more issues. One is the finite element method. I think it will be covered in the second lecture today, so or third lecture today. I will not deal with this one. However, one thing I want to say is that compared to FGTD, compared to method of moments, FEM did not take over the high frequency domain. Even though commercial packages, because they have the built-in routines, they tend to propagate, it's still not that famous because other methods have taken over for various reasons. But in principle, it is possible to use FEM with the only modification is required in time stepping. Whether you want to do direct time stepping or implicit time stepping is the only issue. Advantages would be it can handle multiple materials, arbitrary shape, whereas the disadvantages would be whole domain has to be discretized and we need to do a truncation of the boundary. Other issues are there. Now we'll quickly summarize our observation on high frequency method. There are well established methods. So selection method again based on the salient feature of the problem and whether we have non-linearity, inhomogeneity or special materials like metamaterials are present, then you have to look into your methodology and also on the computer resources, because if you remember the reason for evolution of faster computers were not because of computer science people, it is because of the computational people. Mechanical, civil and electrical people were demanded. So computer people thought they should go to higher hardware. Now unnecessary entertainment to multimedia has demanded higher computation. Storing of data, transfer data has demanded higher computation. Otherwise, the advancement in computer science basically is because of the computational people. In spite of that, now people are having problem with the computer resources, especially when you want to calculate radar cross section of stealth aircraft for that matter, or even an ordinary LC aircraft. We have difficulty because they define the problem in terms of the wavelength. 10 lambda problem, 20 lambda problem, competition between Illinois University and one more company. So we are the present world record holder for the highest complex problem solved ever. Likewise it goes on. So in spite of all this advancement, you may land up in a situation where your computer resource is not adequate to handle the problem. So we have to be careful on that. Application of high frequency method was dealt yesterday. I think we'll skip this one now. So now I want to summarize some of the things and also comment, spend some time on this. Obviously we need to have quantitative knowledge on electromagnetic field, otherwise we cannot do design, we cannot evaluate the health hazard, we cannot understand the physical forces involved. So there is a wide spectrum where I think everybody appreciates that. Regarding analytical method, they are very elegant, yes. However, they have limited capabilities built in, therefore we need to go for alternative approach. Earlier we had analog methods where you try to simulate, scale the problem and do measurement. That's still a possibility, but scaling is possible in certain class of problems and it is case specific, involves lot of time, measurement error and so on and so forth. Therefore, the only way what is left to us was numerical approach. But remember that it's only a particular solution for a particular dimension, particular material property, particular boundary condition. And basic array of numerical methods can be categorized into domain-based method, boundary-based method. As we said earlier, domain-based method, we try to approximate for the governing equation. In the boundary-based method, we try to approximate the source itself and the polarization of the media. Further classification is also possible because low frequency, high frequency. Everything said and done, high frequency people, EC counterparts, always have the pride that they are dealing with complex electrodynamics. It's not necessarily so. To give example, if really somebody wants to analyze dielectric field, first step would be to learn tensor analysis. Then I'm talking electrostatics because electrostatics is considered the least significant component of electrodynamics. If you take the dielectrics, you want to analyze the field inside the dielectric, it's very complicated really. So you need to run tensor analysis first, interaction between you need multiple expansion next, so on and so forth. Things can be complicated everywhere, whether low frequency or high frequency. Just to give example, if you want to analyze corona on the transmission line for the physical process, you need a resolution of micrometers, few micrometers on a problem involving tens of meters. So things can be complicated everywhere. Yeah, if you say just a picture, high frequency problem may look slightly more complicated, but there can be complication everywhere. Then every numerical method has its own advantages, disadvantages. We cannot say this method is good or bad because it has its own intricacies, its own superior points. Therefore, we should decide on the problem in hand which method may be suitable. There are some people who, I will come to that anyway. So this is an important one because people blame the method because they made a wrong choice in the beginning. Then say this method is not suitable, I'm not able to progress in this direction. Then why did you select the wrong method? Then next question, young people some people are fascinated by coding. Yeah, you should appreciate them. But there is some limitation to everyone's ability. They want to code on their own and write codes. It may not be very wise, especially in industrial environment. Never try to write a code on your own because time is equal to money there, nothing else. So whether you learned something, you have done something, not important. You have produced some result or not is important. So in the industrial environment, better to go for a package and learn it because now packages are so complicated. Like a mobile thing. I don't know how to operate my mobile. My kids know it better. Likewise, it is complicated, but we need to learn that. Then, if we have written in-house code, because for research purpose, we need to write code. Either we don't have money to purchase so many packages, or packages cannot be a subroutine in your modeling process which involves physical phenomena. So then when you write in-house code, you need extensive checking, repeated checking, and also you should only propagate the code only for the confirmed or validated regimes, not beyond that, because whatever said and done, I don't think any code to be 100% error free. And you cannot assure that it's independent of platform, so on and so forth. So we need to care on this issue. Then, this is one funny thing about packages. because I advocated for packages, I should also caution here. For every input, package will be a colorful output. But doesn't mean that physical problem is modeled. Then suddenly one person, senior man, appears on my door from local college. He said, you said on that day, ANSYS has large capabilities. I tried modeling point plane. It doesn't give characterism. It doesn't know how to model. Package cannot know anything. It is your responsibility to use the package. And point plane geometry is very trivial geometry to be modeled in any package. He doesn't know. Many people confuse with the axial symmetry, axis symmetry. And one other funny thing is all these packages have beautiful GUI. So they have interface, simply pop down, as per mechanical properties, electrical properties, magnetic properties. The understanding of the user is that, oh, it understood all the physical properties. Finally, they'll select electrostatic. So whatever properties they entered in mechanical and magnetic regime is never been used further on, but they don't realize. I have given all the properties, it has understood. This is one of the complications because, not to deviate, once I had interaction with some well-known company I have not mentioned. They wrote an email stating that they are into electromagnetic braking. Oh, wonderful. It's very good. You should appreciate because they want to do something on their own. Some email, some reply was there. Only 3-line reply was sufficient. Then after 3 months, suddenly they said, come for a meeting. I was wondering, is there I had done something wrong? Or they said, okay, left you, but have you read the email? They said, yes. Then simply they appeared, they gave a presentation. Then what he did was, opened my email, he sent to you, yes. They said, yes. Read the email, he said. The person, the big boss understood. Very sorry, sir, we shall go back. They went back. What has happened? I'm not trying to blame anybody. Our training at undergraduate level is limited because the market-driven, now courses are mostly market-driven. Because a tech program, most of the colleges are getting independency. Then their goal is to make the student marketable. They should get job, on-campus job. As a result, most of the times, electrical engineering has most of computer science and electronics content than electrical engineering content. Whatever we do, forget about the other place. In my own place, I have been told by a senior man that electrical engineering now means signal processing, not power system, no power test, no high voltage. This is the way it goes on. So these people are, well, good people, energetic people, but physical, there's a physical, great package which can model physical model. The right is physical model, but it is basically a model. Whatever input you have given, output will come. You cannot go beyond that. It has no intelligence of any kind whatsoever. Package is not trained in physics like you. It's not trained in mathematics or electromagnetics like you. Likewise goes on. So here, modeling is very important because input, junk in, junk out. Something good in, something good out. That has to be remembered in all these things. And graphical display is very useful in this because we are, as human beings or any other living creature, we are good in remembering patterns rather than numbers. So this graphical display is very important. And good news for researcher is that in spite of all these packages, so much of literature, they have problems from science and engineering which are challenging, which needs more than what is available in these packages or the methodologies. Therefore, our process of improving are looking for new methodologies, algorithms will never stop, will continue to go. With this one, I'll stop my talk. Thanks for listening this abstract one. If you have any question, I'll try to answer. Thank you very much.
Basically, modeling the anisotropic material is challenging task. So, according to you, which kind of method would be best suited for the anisotropic material modeling?
No, not according to me. In principle, anisotropic material can model both the ways, but domain-based method will be easy for you to code and formulate. Because
domain-based method
will be easy, better, because integrals will be more complicated. With I hope you are talking about linear material. Anisotropic is
yeah, exactly.
Then domain-based will still work because most of the times are built in. Most of the FEM formula you see, it's built in for anisotropic material.
Thank you.
Staircasing error is very simple in FTD, FDM, and domain-based methodology. You have one example. Like say I'm trying to model in a Cartesian plane. I'm taking a XY. So no color. Okay. You have got a curved boundary. Then, because I'm sampling the domain or these discrete points, I cannot model this curved boundary. So what I do is I'll approximate this way. Then either this one can be like this, then like this. In other words, curved boundary is approximated to nearest the section of the coordinate plane or the curve. As a result of which, Original curved boundaries modeled with the steps called staircasing approximation.
Good morning, sir.
1 minute. There is also another approximation in FTTD where instead of doing this, what is done is, if the material is different here, it's only for dielectric material, not for conducting. They give the average material property to that cell. That's also possible, but it's still a staircasing error.
So if an error message gets that some PEC cells are found in staircase mode while designing in a CST software, so how to eliminate it?
No, that is specific to your software, nothing to do with methodology, is it not?
Okay.
Package specific. These are package specific problem. For example, lorry. Just to give example, maybe examples are not good. If you in a Maruti car, if you go to first, second, third gear, it zooms up. Where a lorry cannot, because that is the way it mechanism. So you have to look into the package. Difficult. It's not nothing to do with the methodology. Yes, sir.
On certain points, you see, those criticisms could be eliminated if instead of using the Taylor series expansion, you use the method, then the boundary problems, curve boundary and all these would be eliminated because the non-zero dealt on the cross-diagonal terms get eliminated.
I mentioned that, sir. I mentioned. Second one, I did not show. You see, integral approach, you can eliminate many of these errors. Yes, yes. That's the reason they are going to do finite volume method finally. Yes. This process of doing things. Yes. Yes.
And I think for finite elements, this variational approach, at least I would prefer that, because the functional,
Yes, sir.
You don't have to solve the equation, you minimize the functional and the energy functional, and you get the solution of the equation.
But teaching the classroom, Galerkin method is very straightforward, because if you say variational, calculus itself is questionable in many places. Variation calculus, we have one more operator delta, one more operator dou by dou t. It's extremely difficult to teach in class. And then there are problems where there is no variational approach possible, because energy is not, energy function does not exist. Artificially you have to add terms and to get it. So as a solely for teaching purpose, and many of these people have gone to Galerkin approach. Personally I like variation approach, because very elegant, physically meaningful approach. But that is our personal.
It gives a sense of insight physics of the problem.
Correct, sir. But if you can define an energy functional for that problem, yes. Then yes.
Hello, sir. Good morning, sir. My question is related to cavity of a resonating device. So, if I want to realize the things better inside the cavity, so which method I should prefer?
I'm not high frequency man. High frequency people can use. If
Okay, sir. Thank you, sir.
FTDT comment. So actually, when we have a problem which has huge boundaries, for example, lightning, right? I mean, we can't imagine to have a kind of boundary conditions applied there. So which method you mostly preferred on that?
No.
We have huge boundaries.
No, if you are modeling trying to model the lightning or effect of lightning.
No, effect of lightning on some object, maybe say a plane, aircraft.
Yeah.
For example.
Now in those cases, because fortunately, present belief is that lightning does the object is going to alter the current waveform. That being the case, so and more unless your aircraft is like Boeing, where wave effects can be significant, you can still look with the low frequency problem. Nevertheless, in any case, you can imagine a cuboid enclosing the aircraft, apply a PML and do it.
PML.
Because basically current is not altered by the presence of the aircraft. Current is the same. Current remains, magnetic current is the same. Only the
Pass through his body, right?
whole body, yes. Doesn't matter, no problem. But current is like it's like a lightning was modeled as a current source. Still a current source.
Okay.
Up till now, transmission line people also assumed so.
Okay.
Last 7 year measurement in Japan and our model shows not so. Current reduces by to 50%, it strikes to the phase conductor. That's a new thing coming up anyway.
Thanks.
Thank you.
Okay, if there are no further questions, let us thank Professor Udaya Kumar for the excellent presentation.
So thank you, Professor Iyer, for of course, and there is going to be another presentation in this session. I am really delighted to see many students and faculty getting interested in this subject of electromagnetics, and particularly computational electromagnetics is really heartening to know. I think we are slowly going back to basics, and that is really good. And as you may be aware that in many IITs and IISc also now there are some specific courses being run for computational electromagnetics. I run such a course in IIT Bombay. It is a full 4-semester course on computational electromagnetics, wherein the methods that were summarized in this lecture are taught over a period of 4 months. But of course, it may not be possible for everybody of you to do that course. But local people, there have been cases. This course is typically run in the evening, so you can come and attend. Those who are in and around Mumbai, you can at least attend. I'll be happy to see some of you in that course.